All right, welcome back. This is the lecture on vectors and matrix calculus, I believe. Yes, vectors and matrix calculus. So this is part two of the video lecture series. I'm Professor Wu, so let's get started. We did this already last time, so we're gonna jump all the way to part two. Okay, so we kind of started talking about how we can take derivative with respect to vectors and equations of vectors and matrices. Today, we're gonna continue where we were at last time, and you see, this was like an example of a question that we did last time. And doing these type of finding derivative with respect to these equations are pretty easy. Pretty easy. All we do is we take the derivative three times. First time with respect to x1, second time with respect to x2, and third time with respect to x3. Okay, so that's pretty easy. However, however, most of the problem you will see in machine learning, they don't look like this. They don't look like this. Instead, they look something more like this. Now, y is a vector, x is a vector, w is a vector, x is a vector. Okay? How do we take derivative d dx in this case? Or this one, y is a vector, a is a matrix, and x. Okay? Here's yet another one. A is a matrix, y is a vector, and you might even encounter exponentials of a vector matrix vector. Okay? So in these cases, if they don't look like this anymore, then how do we calculate the derivative d of dx? Okay, so that's kind of like the point today. Even though we know how to take derivative of multivariate, like a multivariate input, very often that's like we see something completely different. Okay, so for this class, these are the equations that we are all going to learn. So there are about 17 equations, which we'll end up going through them. And these are the 17 equations you should really learn how to take the derivative of. Okay. Now, you don't need to know what these functions do for now. You don't need to know for now. You just need to know how to take the derivative. That's where we're going to start. And the purpose of this class is essentially to kind of like get your feet wet on taking derivative on this seemingly complicated equations, but they really are not. Okay. So while a lot of equation we just saw seem kind of intimidating, but most of them are actually, once you look a little deeper, not that difficult. They are simply combinations of simpler components. And once you learn how to take derivative of simpler components, then complex ones are just combination of simpler ones. So for example, let's say we want to take a derivative of this. Okay? This derivative of this. So x is a vector, y is a vector, and the variable is x. Okay, so what we want is df dx, df dx. That's what we're looking for. Okay, so when y is a vector that's known, and x is a variable, so there are two variables, x1 and x2. So then, okay, if we have this, when we want to take df dx, what do we do? What do we do? Okay, what do we do when x is a vector? Well, the answer is the same as before. There are two variables, therefore the derivative, there are two inputs, remember? So the derivative must have a derivative with respect to x1 and a derivative with respect to x2. So, I mean, that's the same as like what we saw before, right? When you have multiple variables, oops, when you have multiple variables, right, then you just need to make sure you do it one at a time. And in the vector format, it's exactly the same. Nothing is really different from the vector format. You still get the derivative one variable at a time. So the key is all you really have to do is multiply the vector out first. Okay? I cannot emphasize this enough. When you see something that looks like a bunch of vectors, all you have to do is multiply everything out. Because once you multiply out, so remember what I told you what y was and x was. So here's y transpose x. Oop, that should be x2. Okay. So once you have this x1, x2, after you multiply them out, you end up getting this equation look like this. And this, we know how to take derivative of this. The derivative is simply you take derivative only with respect to x1 and then only with respect to x2. Okay? So taking derivative of this is easy. And therefore, the key for you to realize is that all you have to do when you look at very complicated matrix vector multiplication, you multiply them out. So this rule applies for any, as the first step of any vector matrix derivative. After you multiply them out, it's just an equation. And with that equation, you simply take the derivative one variable at a time. Like after you multiply everything out, then you take the derivative one variable at a time. Okay? As long as you know how to take derivatives one variable at a time, then you can basically take derivative of any complicated equation, even though they're written in terms of matrix and vector format. Okay, so um, and then so the first step I said multiply them out, and then second step you take the derivative one variable at a time. And the last step is you basically, once we calculate the derivative, we then put the results back into vector and matrix format. This part is a little bit confusing, but we'll go back together. So these are the three steps that you would do, okay? If you don't know how to, you don't already know. Because if you do it often enough, you see a pattern and you can just memorize the result. But if you don't know what to do, these are the one, two, three steps you can always take and you'll always work. So let's look at the simplest function. It's called a linear function. A linear function is exactly what we just looked at, right? Well, when we want to take the derivative, like I told you, all we do is multiply them out. And then when we take the derivative with respect to x1 is 2, and derivative with respect to x2, which is 1. So we now have the derivative. Like it's really, really that easy. Okay, so that was step one. Step one is when you multiply them out. Step two is to take the derivative. Now I told you there's one last step, step three, which is you put the solution back in terms of the original vector. So now if we look at what the solution derivative, well, what is this in relationship to its original problem? Well, you'll see that this is actually y. And from this, you realize that, okay, if we take the derivative with respect to y transpose x, right, then we got 2, 1, which is equal to y. This allows us to conclude that when you take the derivative, y transpose x, the solution is simply y. Okay? And this actually happens regardless of the dimension. So anytime you see this, I just basically show you that the derivative is when you simply get rid of x. Okay? If you remember that, you won't have to do it again. But if you don't remember this, then you can always follow the three steps: one, two, and then three. Right? If you now, like I said, you really just need to remember this final conclusion, right? But if you know steps one to three, you can always reach this. So, and I said that this is regardless of the dimension of data. You can essentially use any vector. So let's try it. Over here, this is the equation. However, the only thing that's different is now we have a different vector y and different vector x. Now it's three dimension, right? Now I want you to pause, essentially follow step one, two, three, and then you will see that the solution df dx is simply just y. Okay, so use the step 1, 2, 3 we just did and see if you can arrive to this conclusion. And this hopefully will convince you that whenever you see this and you want to take the derivative, you simply get rid of the x portion. Okay? All right, try to find a derivative for a function. So now that we've gone through the steps 1, 2, 3. 1, 2, 3. Right. One more time. Step 1 is multiply it out. Step 2 is take derivative one derivative at a time, one at a time. And step 3 is put it back into matrix format. This one is a bit tricky, but give it a try. Pause the video and you can go from there. All right. Okay. So hopefully you pause the video. I'm going to continue. Now, this one, remember, if you were to multiply them out, then you're going to get this equation. And this equation is really easy to take derivative of. With respect to x1, we're going to get this. And with respect to x2, we're going to get this. Now, the hard part is how do we put this back into matrix vector format? Well, notice how these are x1, these are x2. Then we can pull the x1, x2 out. So it's now a matrix multiplication. Right? And then this part is the tricky part. You can actually pull this right here is equal to this plus this multiplied by this. And it turns out that after you do the split, this is simply A transpose A. See? This was A. Notice how we were able to reconstruct the original matrix. So the derivative is simply A transpose A times X. Okay? And this turns out to be always the rule when you see this. This is called the quadratic form. When you see this, it's always, you get rid of this x, A transpose plus A times x. Okay, this is always the rule. So once again, if you don't remember this rule, you simply can follow the 3 steps. Multiply them out, and then take the derivative one variable at a time and reconstruct the original matrix. Okay? All right. Here are 3 more questions. Let's take a second and see if you can solve these. Okay? Ideally, you don't use the slow way. You try the fast way because you remember what they are. But if you get stuck, you can always fall back on the slower way of 3-step process. Okay? Pause the video. We're going to go on. Okay, I wrote the solution for that out. Okay, so we actually solved this right here. Okay, so this problem here has a specific name. It's called a multivariate Gaussian, and like as you can see from the solution, this right here is the solution. It's not that hard actually, because if you know the derivative of this, remember it's A plus A transpose X. Okay, if you know the derivative of this, then we can simply say df dy. We let y equals to minus x transpose ax. So therefore, f of y is equal to e to the y. And df dy is equal to e to the y. And then dy dx is therefore equal to the derivative of this, which is minus a plus a transpose x. Okay, now you simply multiply them together, which is the result. The multivariate Gaussian, that's how you calculate it. The PCA objective. This one, we will run into it. The PCA objective looks something like this. We solved something very similar to this previously. All you need to know is basically how to take the derivative of the quadratic. This is called the quadratic form. And this is another quadratic form, and this is a constant. So the quadratic form here is easy if you remembered the solution, which is A plus A transpose times X. So we did that. And over here is, well, lambda, right? So the derivative of this would be I plus I transpose X. And since I, ah, I haven't defined I here yet. I is equal to identity. Looks like this, which is equal to the transpose. So I plus I transpose is equal to 2I. Okay? So, well, we did a very similar one here. So this part is how I end up getting 2 lambda x. Actually, this part should be lambda ix. Okay, so the PC objective was very similar to this one that we did. Okay, trace of quadratic form. So the interesting thing that I think I want to show you here is that the trace of actually the no the trace of a one dimension vector is simply itself, right? So remember, trace of a matrix is you add up the diagonal. However, if you only have one element, like 5, then the trace of one element is simply 5. Now, over here, if you have a trace of this, since the result of multiplying them together is a number, therefore the trace of this is simply equal to this. Right? And this implies that the derivative of trace of the quadratic is simply the derivative of the quadratic. So if you know the derivative of the quadratic, it's the same as derivative of trace of the quadratic. Hmm? The second, what makes this interesting is that the second property we're going to learn, trace is rotation invariant. What that means is you have trace. If you were to rotate this right here, right, it's actually equivalent. And then you can rotate again, put the A right here. So if you just keep rotating, they're actually all equivalent. Therefore, if you take the derivative of any one of them, it's equivalent. So trace of this, trace of this, trace of this, trace of this. Okay. So once again, the trace of this is actually just equal to the trace of the quadratic without the trace. Okay. Okay. The next one is called a regression objective. This is probably one of the most important objective that you will need. You will probably take a lot of derivative of this. So yeah, why don't you try take out a piece of paper and see if you can do this one. Okay. Hopefully you pause the video. I'm going to continue. The linear regression objective is what we just looked at, and and it's actually not that bad. When you want to take the derivative of this, you simply treat this portion as a variable. So you, like, let's treat that as like z or something. And therefore, when you take the derivative, 2 goes down and 2 minus 1, right? So the df dz is equal to summation of zi. That's it. Yeah, summation of zi. Now we take the derivative of what's inside here. Z is equal to w transpose xi minus yi. So what is dz dw? Because it's the variable is with respect to w. Therefore, this is a constant, so this is gone. And the derivative, this is a linear, therefore it's xi. So now all we have, we multiply them together. Summation of z is w transpose xi minus yi xi. I equals 1 to n. Okay? Which is seen right here. So that's how you can do it. That's the solution. Okay. The next function is called the ReLU function. The ReLU function is looks like this. It's a function where if you put a variable in, as long as it's less than 0, the derivative, you can see, it's not going up or down, so therefore the derivative is 0. And anything that's above 1, the derivative is equal to 1. So the ReLU function is important today because it is a really, really important function inside neural networks, modern neural networks, and it's basically used everywhere. So ReLU is a really, really important function. And so now, if we want to take a derivative, we now know ReLU of x, and we want, if f of x is equal to this, then df dx must be 0 or 1. If x is less than 0 and x is greater than 1, right? So that's what the derivative will be. So now we can essentially split the problem we have and call that q. W transpose x is equal to q. Okay, so now we know that the derivative of q will be 1 if W transpose x is greater than 0. So this is called an indicator function, which says it's 1 if it's greater than 0, and if it's 0, then if this condition is not met. So the key is basically I should have explained the indicator function first. So indicator function is a function that if this condition is met, then it's 1. If it's not met, then it's 0. Okay? So that's how the ReLU is defined. If this is if 1, if whatever's inside the ReLU, W transpose X, it's 1 if it's greater than 1. And if this condition is not met, then it's 0. Okay? So therefore, basically we took the derivative of what's outside here with respect to q. So this is df dq. And now dq dw, we simply take the derivative of this with respect to w. So this is a linear form. Then with respect to w, it's just x. So that's where the x came in. All right, so that's dq dw, df dq. So this right here is the derivative for the ReLU function. Okay. The next one is a sigmoid function. Sigmoid is pretty easy. A sigmoid function looks like this, and this is equal to 1 plus e to the minus x to the negative 1, right? The negative 1 is the inverse. So we simply put the negative 1 down and subtract 1. So now negative 1, negative 2. And then we take the derivative of what's inside, which is e to the minus x, and we take the derivative with respect to negative 1, we get this. So this right here is equal to the sigmoid function. Why don't you take a second, pause the video, and see if you can understand how this came about. Okay. Now I use the chain rule much faster now. I can do the chain rule in my head, but if you use this is essentially an exercise of chain rule because there were a lot of chains together. Now, this is the derivative for ReLU. No, not ReLU. I mean sigmoid. And normally they do a lot more manipulation to put it in a nicer form. But you can look at this yourself if you're interested. In textbook, they tend to represent ReLU's derivative like this, but they're the same. They're equivalent. Now, sigmoid was really important back then. It's still pretty important today because it was the original function used inside neural networks, what they call the activation function. Nowadays, they don't use sigmoid as much. Okay, wow, we have a lot of equations to go through. So the next one is called L1 norm. The L1 norm, we learned the norm, I believe, last class, right? We learned the concept of norm. And L1 norm if you have multiple dimensions, x1, x2, x3, is the one where is you're a pedestrian, right? You're a pedestrian, so you basically just add up the length of each dimension. So L1 norm is x1 plus x2 plus x3. Or if it's two dimension, and that's it. You're just adding up the absolute value of everything. Now, the absolute value function looks like this. So the derivative for any value less than 0 is simply -1. And the derivative for any value greater than 0 is +1. Therefore, all you really need to look at is the sign. So derivative with respect to x1, you say the sign. If the sign is positive, then it's equal to 1. If it's negative, then it's -1, right? And that's actually what a sine function does. The sine function looks at the sign. If it's positive, it returns a 1. If it's a negative, it returns a -1. Okay? So so basically the derivative of L1 norm is a sine function. And when you need to find the derivative of any given point, you simply put the point in. Okay? Okay. Now that we've done L1 norm, let's do L2 norm. The derivative with respect to L2 norm, well, L2 norm is the one where you find a hypotenuse, right? So it's a Euclidean norm. So it looks something like this. So the square root can be written as to the power of 1/2. So now, if we want to find a derivative, we simply put 1/2 here, and then 1/2 minus 1. Therefore, it's minus 1/2. And then we take the derivative of what's inside. So what is the derivative with respect to x1? Well, 2x1. Derivative with respect to x2, 2x2. And then I can move, let's see, I can rewrite this as 1 over square root, right? So 1 over the square root of this. And the 2 cancels each other out. And then all we have is left is this x vector. So we can rewrite this in the original form. This right here is just x. This right here is the L2 norm. And that's why I end up having 1 divided by L2 norm times x. Okay? So finding the L2 norm is not bad. You can just memorize the final result, or you can take the derivative. Okay? All right, the Gaussian. Okay, now this is the Gaussian distribution is used very often, and now we're coming to the end. I know we're like grinding through every one of these really fast. Maybe I should yeah uh, yeah, we have to. Like these are basically the functions we got to grind through. All right, so it's just one dimension. So Gaussian is easier because we're not going to do the multivariate version. And this Gaussian MLE objective looks like this seemingly complicated equation. And taking the derivative of this, you might think, wow, this is like really complicated. But if you know a couple tricks, you could drastically simplify this equation and make it look really simple and easy to take derivative of. So the first thing you need to know from this is that the product symbol. So the product symbol here, what does that mean? Well, if you have product symbol, that means like the summation, instead of summation, you do multiplication. So that means x1 times x2 times x3. So if it's 1 to 3, it's saying that all the way from 1 to 3, all the x from 1 to 3, you're going to multiply them together. Okay? So that's what the first thing you need to recognize what this means. The second thing is the log of two variables multiplied together has another special property. So if you have log of x1 times x2 is equal to the log of x1 plus log of x2. Therefore, when we have this multiplication where you have multiple of them, right, log of all of these is equal to log of x1 times x2, x3. And remember, when you have them multiplied together, we can split them into summations. And when you split them into summation, then it's a summation of log of xi. What that means is when we have a product inside the log, we can move this product outside as a summation. Okay? And they will be mathematically equivalent. And this summation actually drastically simplifies things. Okay? And lastly, you need to learn two more properties. One is if you have a log with some power, this is equivalent to moving the power to the front, like this 4. And the second one is log of e is equal to 1. Okay? This is based on the definition of how log works. Okay? So once you understand, like take a second and think about these three properties: multiplication, splitting of log, and the two properties where log e is equal to 1 and moving the power. Keeping these in mind, we can now drastically simplify this equation. Okay? So first, what we do is we move this outside as sum. So notice how over here is multiplication inside the log. Oh, this should be log, and then we move it outside. Okay. Once we move it outside, then if we're gonna take derivative with respect to mu, notice how this has no mu. Oh wait, 1 second. 1 second. I skipped a step. So first I move the product outside as the sum. And then after that, with the log, you can split. You have two things multiplied together. You can split them. So I split log of this plus log of this. Okay. After, because log of xy is equal to log of x plus log of y, right? That's how I did the split. So after I do the split, notice that there's no mu in this term. And therefore, when we take a derivative, this is a constant. So this is just 0. So we drastically simplify that. And next, notice that this is an e to the some power. So with log, we can move the power to the front of the log. So if we move the power to the front of the log, then our result is log of e, which log of e is equal to 1. So we can cancel that. So that really complicated equation is suddenly now pretty simple. Now, since this is a constant, so we can move that out. We can also move the summation. So we're really only taking derivative of this function, which is really easy to find. Okay, the derivative of this, like 2 goes down, cancels out with this 2. 2 cancels out, and it's just this multiplied by -1. So the minus cancels out. Okay, so these really, really complicated equations might seem complicated, but there are ways to simplify them if you know the log rule. Okay, now that I know that was a lot to go through, all these like log properties, so I'm going to give you a chance to practice. This is the uniform distribution objective, right? And it has something very similar. Instead of log, let's use ln here and see if you want to pause the video and see if you can essentially use all the rules we did on this problem and see if you could find a derivative yourself. Okay, pause the video, or we're going to go on. I wrote out the solution. Okay, so that was a lot of equations we went through. We in a previous video we did the univariate, and essentially I showed you how you are able to um, check your answer, right? Basically, you can write out your derivative and then get the Python version of the derivative. So if you can compare the result, you can confirm whether what you got was correct. So you can basically confirm whether your derivative is correct or not. So over here, you can also use autograph for this. Autograph works for both univariate, or multivariate. So over here, remember this given this function trace of W transpose AW. That was one of them that we went through, right? If you are able to, if you're able to find the derivative of function will equal to this. Okay, so let's see. So over here, it's saying that the function is trace of the transpose times A. So, okay. So the transpose of this, and we do the dot product here, and then we do the dot product here. So that's equivalent to this here. And then once you have the function, you can define the grad function. So this is the Python version. And we know the derivative is equal to this. So basically, I print out the derivative of the Python version and the derivative of my own version. And you can see that the gradient is exactly the same. So the process is the same. The only thing that's so I wrote a whole bunch of examples. So this is the quadratic form. This one is the exponential form. So you want to you in your homework you'll be asked to essentially confirm your results for these various equations, and you can follow these steps. Now here's another one. I did the ReLU for you guys as well, so you can kind of like see how I did it and follow the same steps. The only difference that you need to keep in mind with the difference between single variate and multivariate is that bunch of functions in NumPy they don't work anymore. So such as transpose, right? If you want to write transpose, they changed it to transpose. Okay, so this is not the same. This is much easier, but in AutoGrad they only allowed this one. Or the dot product. When you have x dot y, great. I love that form. But in AutoGrad it also doesn't work. So these like dot, you will have to use np dot. Okay. So there are other ones. Just be aware that if one of the function you were using stop working when you're using doing the AutoGrad, that's the reason. That's the reason. Okay. All right. So this let's consolidate today's knowledge. For the final class exercise, you want to essentially find a derivative for each one of them. Once you find a derivative for each one of them, you want to once again pull out Python and confirm that they're correct. Okay? And I think that's it for the day. All right. Some of the coding solutions I've written for you. So if you really struggle, like how to do this, you can kind of look through the coding solutions and see how this is done. Okay. All right. That's it for today. Thanks.